So to stay on time, our next speaker will go ahead with Andre, is going to address us. He's with the University of California Cooperative Extension. I'm located there down in Ventura County. Andre has his master's degree in agronomy and soil science from Auburn University. And then previously to that, he was at the University of Sao Paulo in Brazil. Andre has a real active research and extension program and is passionate about helping farmers and growers and consultants improve their irrigation and their nutrient management decisions. And as you hear Andre, you'll realize that how excited he is about the work that he does. He took on an interesting project where he's assessing the accuracy and the precision of soil chemical analysis performed by 8 agricultural laboratories. And that's a question that we always wonder when we get results back from the lab. Can we count on these results? Are they really giving us the information we need? So, Andre, we look forward to hearing from you and finding out what you discovered in your pursuit of the right numbers.
Right, sounds good. Thanks for the introduction, Rob. Good morning, everyone. I'd like to start this presentation thanking FRAP's Conference Organizing Committee for the opportunity to share the data here. And so, yeah, let's go ahead and get started. I'd like to also start with acknowledging the people involved in helping and making this project possible. Robert Wheeler with the ALP program, and he used to be the former UC Davis lab director, and Bob's been very instrumental to with multiple steps of this project, so I appreciate his help. And also project cooperators Steve Orloff, Dirk Holsters, Tim Hartz, Anthony Luna, Aaron Wingate, Steve, Dirk, and team helping in the initial stages of how to set up this project and provide some great feedback, and then Anthony and Aaron at specific stages of the project. Also, I'd like to thank Ben Faber here from our office in Ventura. He's been very helpful providing feedback to the project. And with that, this presentation will cover some context in soil chemical analysis, and then I'll talk about the material methods, results, and a summary of the data collected with this project. So, well, a little bit of a context of soil chemical analysis. I'm sure most of you are familiar with it, but I'll go over then and then jump into the project itself. So an accurate soil chemical analysis is the cornerstone of an efficient nutrient management program. Without a reliable soil test result, significant mistakes in fertilization programs can occur, resulting in under or over fertilizer recommendations. This can dramatically affect profitability and can potentially have negative environmental consequences. Skilled soil analysis can also bias the data and finds of soil fertility and nutrient management research, and this is where I'm coming from with starting this project, questioning how good actually were the lab results. So in some cases, dozens or hundreds of soil samples are collected from a single site and submitted to a laboratory for fertility assessment. And deciding which laboratory to send a sample can be a daunting task. So unfortunately, there are no public data reporting the accuracy of the analysis performed by ag laboratories, and there isn't a true certification program in the US. Current proficiency programs like the ALP, or the Agriculture Laboratory Proficiency Program, and the NAPT, the North American Proficiency Testing, they are not mandatory and they do not guarantee quality control. Lab users deserve to be able to assess the quality of a laboratory before committing and trusting in its results. So the objectives of this study were to assess the accuracy and precision of soil chemical analysis performed by 8 ag laboratories, and to provide lab users with science-based information of the quality and reliability of these laboratories. So for the material methods, the but this is a basic information that it's very important that you understand how we conducted the project. Basically, we purchased 4 different reference soils from the ALP program. Those are represented by these 4 buckets in here, and that's actually how they come in buckets. And these are the soils that we purchased from them. So we'd collect a sample from each of these soils and send them to each of these 8 laboratories, 7 in California and 1 in Idaho. And then we did that 3 times, December and then April and June, to also assess the precision of the laboratories. And we asked the labs to analyze these samples for basic soil fertility, and those are the analyses that were most common for most of the fertility packages when the lab offered that package. So a little context of what a reference soil is. Reference soils are soils collected by the ALP and analyzed by at least 30 credible laboratories, over 90 times total for each sample. Basically, the way it's done, that they go to a site, collect a certain amount of soils, and then they dry it, grind it, sieve it, homogenize it, and sometimes they dry it again and grind, sieve, homogenize, and they do that a couple times, so that material is very powdery looking and very well homogenized. So each of these samples then, they contain a nutrient content that's determined by the median of the 90+ analyses that were submitted to the ALP program. And these medians from the ALP program that you receive when you purchase these reference soils, they were used as the reference of nutrient content for this analysis. In this slide in here, I'm sure most of you are very familiar with it. I just want to emphasize the difference between accuracy and precision. Accuracy is how close, in this case, the analyses were from the accepted value, which in this case we're considering to be the ALP's median. And then the precision was how variable the analysis of the same soil were across time. Okay. Let's jump into the results. In the next few slides, I'll show some graphs exemplifying what we obtained as far as the data for this project, and after that I'll show a more complete analysis of the data. What you see here is extractable potassium performed with the ammonium acetate extract for soil A. And then in the y-axis, you see the concentration in ppm, and then on the x-axis, you see the laboratories that we assessed. So we have laboratory A, 1, 2, 3, so forth. And then for laboratory 1, for example, we have the result for exchangeable potassium for soil A in round 1, 2, and 3. So this is the same sample, same analysis, sent to the same laboratory, providing these results in here. And then we have, with the dashed line, is the median provided by the ALP program that we consider to be the true value. And the solid horizontal lines above and under the median are 2.92 times MAD. And MAD is a sort of standard deviation. So this is how the MAD is calculated. The difference between each value of those analyses, the 90+ analysis minus the mean divided by the, well, you get the absolute value of that, add everything and divided by the number of observations. So that gives us an idea of, you know, how acceptable, at least this is what a standard used by the ALP, and I like that standard, and this is how we will be looking at the analysis for this project. So what we can see here is that for laboratory 5, for example, you had The first round providing a value that's significantly lower, like a fourth of what the median from the LP is, and then the next two analyses were, performed quite well. And then you see here laboratory 8 with a precision issue and also an accuracy issue. So let's move to the next graph. This is again exchangeable potassium with the ammonium acetate method for soil C now. And then you see laboratory 2 again providing values that are under. If you go back to the previous slide, you see those values are under the range that we use for acceptable values. And then you have the same trend observed in laboratory 8 and 5 in here for issues with precision. Let's move now to, this is OSMP for soil A. And we see most of the labs got it right most of the times, but we do see an outlier here. This is pH for saturated paste for soil C. And then we see a good amount of labs got it right, but certain labs often get it off. Now, before I jump into some of these, the summary of the data analysis we performed, I'd like to point out that there were actually some inconsistencies between lab results and the reference soils, and that was the case for iron and manganese. So I understand that happens because of the processing of the soils. When they are dried, they tend to oxidize, and then their nutrient content in this case increases. And also for the nitrate, this was really difficult to understand why this happened. That for practically all laboratories, the nitrate content increased from the first to the second to the third round. So the reference soils, they got here in Ventura are really dry, and they're really powdery. But before they were sand, the ALP program actually wetted them and then dried them in a matter of a couple hours in order to have their appearance to change to look more like a soil sample. Otherwise, they'll just be looking like a powdery material, which is usually what the laboratories receive when they perform a analysis, when they affiliate to the ALP or the NAPT programs. And just also to mention that in that case, they know they're receiving the reference soil samples when they're assessed by these proficiency programs. In our case, I don't believe they knew the samples were being sent. They were reference soil samples. So when they receive a sample from the ALP or the NAPT program, they can run that analysis multiple times until they get an acceptable result. Now, to do a sort of a ranking of how these laboratories performed as far as accuracy and precision, we chose these 8 specific analyses in here: OSMP, extractable potassium, calcium, extractable magnesium, EC, pH, sodium adsorption ratio, and DTPA zinc. So a little bit of the accuracy method. We considered a failure for each analysis if the results were higher than the ALP's median plus 2.9 times the MAD, and again that's a sort of standard deviation measure. And also we considered a failure if those values, the values of the analysis were lower than the ALP median minus 2.9 the MAD. Which, and by the way, this is basically what you recently saw in the previous graphs, those ranges between the solid horizontal lines above and below the median. So the overall precision score was calculated as a proportion of unflagged analysis to the total number of analyses, meaning the analyses that were acceptable divided by the total number of analyses. So let's just say if a lab performed 100 analyses and 10 analyses were flagged, that means the score of the laboratory was 90%. And then for the precision method, we calculated a ratio of the standard deviation to the mean for each analysis in soils across the 3 rounds. Basically, we're trying to assess how they changed with time for the same analysis, same soil. So use the relative standard deviation, which is basically the mathematical description of what is described above it. So non-acceptable analyses were flagged as outliers based on the ALP standards. So, and I can talk a little more about that in the next couple of slides. And the overall precision score was calculated as the proportion of unflagged analysis to the total number of analyses. This is a summary of the results for Lab A. For example, when you see all the analysis in here, OCMP, extractable potassium, and all the soils. Soil A, B, C, and D. And then we have the medium, med, but I really don't expect you to read these values. This is just to illustrate how this was performed. So we have the first round, second round, and third round. Again, for laboratory 1. So when you see these red values in here with L and H, those are flagged analysis. So for each round, we calculated a score, and then the average of the 3 scores for the accuracy was considered the overall accuracy score or overall proficiency score. And then the RSD, or with the relative standard deviation, among those 3 analyses were calculated, and certain values for specific analysis were attributed based on ALP standards, and then again they were flagged, and the proportion of flagged analysis determined the overall precision score. This is the final result of those analyses. So basically what you see in here is a score for accuracy and precision for each of the laboratories, 1, 2, 3, and so forth. So those with the blue circle are laboratories that performed well or above 70% in accuracy and precision. What stood out in here was laboratory 7 with the best grade, and then we have laboratory 1 and 6 also with the second best grades. Laboratory 7 also only participated in rounds 1 and 2 because we didn't have sufficient funds for that, but nonetheless the accuracy was pretty good. Now those are the labs that presented poor results, specifically laboratory 8. So what this score here tells us is that only 20% of the analysis from laboratory 8 presented accuracy values that are acceptable to the standards we assessed this analysis, these results. And the precision was actually a little worse. Only 17% of the analysis presented acceptable precision. And then we had laboratory 2 also presenting very poor results, and some of the laboratories fluctuating here between almost decent and decent to poor performance. And unfortunately, due to university policies, we cannot disclose who laboratories 1 to 8 are, but this really gives us a good idea on how to choose a laboratory and provide some feedback to people who are trying to decide what way to go about choosing a laboratory. So, in summary, although all labs presented certain inaccuracy and precision, some stood out. Laboratories 2 and 8 were consistently inaccurate and imprecise throughout the analysis and soils, specifically Laboratory 8. Laboratories 1 and 7 were the most accurate and precise, with laboratories actually 6 also being quite precise, and laboratories 3, 4, 5, and 6 presenting, or 3, 4, and 5 presenting fluctuating accuracy and precision, and laboratory 6 presenting fluctuating precision. Other observations for these studies are that the main challenge of the industry is consistency. Consistency in the methods of analysis, consistency in reporting the methods, the reporting units, and of the interpretation of the results. I firmly believe that lab users could advocate for the lab's adhesion to a proficiency program where there is a standard for expected performance. And with that, we could launch the poll questions. Yeah, that's quite interesting. I can't imagine that anybody would not, or as a lab user, would not want to have the labs to participate in a proficiency program, right? That assures the quality of the laboratories, but maybe those people didn't understand the question. But for the other question is, are laboratories in California required to participate in a proficiency program? They're not. So those participations are voluntary, and basically they can participate in a certain year, and they post on their website that they participate on that specific year. But you know, if they don't get a grade, they just don't post that they participated in the, or if they don't get the passing grade, right, from that proficiency program, they won't post that, and you just won't know what's happening there. So yeah. And that's it for my talk. And also, I put in here Bob's contact information in case anybody wants to contact him directly. He's been a huge help for the project.